Once again welcome to this lecture. This is in my last lecture just I have completed how to estimate the quantity of seepage through the body or the water returning structure, and then just I have shown the application of flow net. And if I can draw the flow net and if I can make a equal potential line number of at equidistant and with a equal drop, and if I can draw a few flow lines, and between the flow lines I can imagine this is a flow channel. So, each small flow channels I can imagine. So, number of flow channels I can count from the figure, number of flow equipotential drop I can also count from the figure, and head difference between the upstream and downstream also I can find out, and K for the soil will be known. So, based on that we can find out the quantity of seepage which will be equal to K into H times N f by N d. So, N f is the number of flow channels and N d is the number of potential drop. So, that was the thing I have discussed just previous lecture. Now, how to draw the flow nets? It is not a very easy task, as it has to be, as I have mentioned that while deriving that equation, one thing is from the property of the flow line and equipotential line, we have mentioned that they generally meet at right angles to each other, and also that we have mentioned that we can try to make, while drawing the flow nets, we will try to make either square blocks. The size may not be the equal, all blocks may not be equal size, but while each block looks like look like a square, that means all sides of the block approximately equal. If I do that and follow that, then one can draw the flow nets. And in fact, this before drawing that, one has to identify the initial equipotential line, initial flow line, which are those based on the inspection of the this is the suppose dam structure, and this is the body, and here actually suppose something head is 0 and here head is this much, then that means from this to this distance head is constant, from this to this distance head also constant. So, that means this can be considered one equipotential line, this also can be considered as one equipotential line. Now, water will be at this point, we will try to move along this. So, it is considered as this as a flow line, and if there is a obstruction, then water generally through this actually it will go and it will go like that, that is one path. So, that can be considered as a flow line, and then also water from here it will move along this also, that can be considered. So, that means we have fixed one flow line, this is equipotential and this is equipotential line. So, these are the things. So, now I can, this is equipotential line, this is also equipotential line. Now, if I want to draw a flow line should come out right angles from here. So, starting point should be right angles, and when the line will go like this, and when there is obstruction it will be not, it will not go straight and come down like that, it will smoothly pass over this and it will reach here. So, that is the first trial of this is one flow line, this may be the second flow line. If I get this second flow line, then I can proceed, as I have mentioned, I can find out what is the head difference, from there I can find out del H, and if I want to draw suppose 10 equipotential line. So, I have to 9 actually there will be drop. So, there will be 9 drop, equally I can divide and I can fix this way, suppose this was 1, 2, 3 like that, and there will be number of them, so I can fix it, and then accordingly I can start satisfying this right angles requirement and making square that requirement. I can complete those initial, and slowly I will extend this one. Suppose next stage I will extend this one further, I can imagine another flow line from here. This was a potential line, and this is a flow line meet come out right angles from here, and I will extend slowly this and this, so that they will meet at right angle and same time this become rectangle square, this all become square. So, like that I will draw another line like that, and then it suppose was here, it ended here, and further I will imagine another flow line, and I will extend this side and extend this side in such a way that always it will make nearly square, and along this there will be another equipotential line. So, like that once you complete this, so now I can count how many potential drop. There will be 1 from here actually, or total head 1 2 3 4 5 6 7 8, there will be 8 drops. So, your del H will be H by 8 sorry 1 2 3 4 5 6 7 8. So, it will be 8, and how many del H become this H by 8. So, N D is actually 8, and N F will be how much, how many, this will be 1 2 and 3, and last one you can see it will become narrow. So, approximately by eye estimation, though it is becoming bigger and bigger when you are going away from the body, but this one need not be considered as a full flow channel. So, it can be partially 3.4, 3.5 like that. So, N F can be considered partly 3.5 suppose. So, then from this figure I can find out Q equal to K is known, H is known there, and N F they suppose 3.5 and N D suppose is 8. So, from this equation I can find out the Q. So, this is the procedure how to draw the flow net, and this is the equation finally to use for calculating the seepage. So, this is of course, is a not a very easy job. One has to do large number of trials and practice, then only one can get this type of flow net. So, now most loose deposits are probably isotropic. That means, if the soil is a loose condition, then when flow takes place, then flow all direction will be almost equal. That means, value of permeability in the horizontal is same as in the vertical direction. But actually, in the practice, when there will be this type of structure is constructed, generally it will be filled in layer and then it will be compacted. So, when we do this, then what happens, it vertically it is getting compacted, horizontally it may not be that much. So, because of that, it is seen that whatever the amount of permeability is in the horizontal direction and whatever permeability in the vertical direction, they are not same, they are significantly different. In fact, this is the value in the value in the vertical direction is usually 1/5 to 1/10, that means of the value in horizontal. So, horizontal direction whatever value is, say 1/5 or 1/10 of that value. So, that means horizontal direction is always higher than the vertical. So, this is the permeability is that means they are not same, k x k y is not same. So, the general differential equation flow generally we have derived when k x k y k z is not same, this is the general equation, and if it is 2 dimensional, if you consider, then this is the generalized equation. So, this equation now if the k x and k y is not same, we will not be able to draw the flow net. When we have drawn the flow net, there we have shown that k x equal to k y or k z, because then only we could draw or apply the law and we could draw the flow net. But if it is different, then we will not be able to draw the flow net. But there is a solution, we will be able to draw the flow net by you have to do something. What is that you have to do, that we will see in the next subsequently. Now, unless k x, as I have mentioned that unless k x is equal to k z, the equation is not a true Laplacian equation and cannot therefore be solved by a flow net described before. To utilize the method, it must be modified for an equivalent homogeneous system. That means, when k x and k y is different, and suppose this is the soil mass and the k x value is this, k x this is k x and this is k z, and if they are different, then I cannot apply that. So, what we can do, we can consider an equivalent k, or we can convert this geometry in such a way that automatically if I take these two are equal, then also our calculation will not affect, or it will not be. So, that way actually that means we have to try to make or transform the actual structure into an equivalent structure. So, that considering the variability in permeability in two direction. So, to do that, what I can do, I can take this equation, original equation, and I have taken divide by k z. So, k x by k z and k z get cancelled, k x by k z del 2 h del x square plus del 2 h del z square I am getting here, and then if I this can be converted actually del 2 h del x t square del 2 h del z square equal to 0. Now, this is actually Laplace equation we have converted, and your coordinate axis there actually it was x and z. Here your coordinate axis is x t, this was before x and z. Now, my equation is x t versus z. Now, what is x t? What way it is different from x? That to be seen. So, that while doing this, we have substituted 1 by x t square equal to k x by k z into 1 by x, then only we could get that. And then x t, that means what is the x t with relation with x? X t equal to x into under root k z by k x. So, this is the one, that means I can keep vertical direction or in unchanged, but horizontal dimension x t I can convert into x t. How to do that? That the value in corresponding, using the corresponding value of permeability in two direction, and that way I can convert. So, if I once I convert, then what will happen, that system become homogeneous in terms of x t and z, and then I can draw that modified or transformed section. I can draw the flow net as described before. That means, assuming that is homogeneous and satisfying those conditions, that means flow line, equipotential line meeting at right angles, and also while doing flow net we will try to make a square blocks. That means, each block should be side and width, length and breadth will be equal, and if I do that, then again going back to original section, I can show that that same equation is valid with little modification, that we will see one by one. So, now the equation modified is now a Laplacian and involves the two coordinates variable, one is x t and z. Originally it was x and z, now it become x t and z. It can be solved by a flow net provided that the net is drawn to a vertical scale of z and a horizontal scale of x t equal to this. So, this is the change actually. So, sorry, the horizontal scale has to be changed, the x t equal to x into under root k z by k x. So, if I do that, then how that equation can be utilized or used, that I have to see now. I have taken now the two sections. This was the natural section. Suppose x equal to, this is x actually, this is the x, and maybe in some relation it is there, and this is y direction is a, and this is transform a in this form, and in this transform, when you transform this, the same equation is valid, that means this exactly as before, that means I can use this equation q equal to k into h n f by n d. That means, once you draw the transform section below the structure, if I draw the flow net, I can count number of flow channel, number of potential drop, and H already known and K is known, then I can find out the flow. But doing that, to how to transform this, the only problem is what value to use for K, that K value, what value of K to be used when I will do this. So, when I am converted transforming the section, the K will not be the same, K should be different, because K was originally different in two different directions. So, to do that, we will this sketch can be used. You can see this was the original and this is the transform. Original was A times under root k x by k z and transform is A, because we have shown previously relation between x t and x. This is to prove only, this value can be anything and we can scale it to this one in any value, but to prove I have taken this way, so that if I transform this way, then your equation can be shown properly, that how this is valid. Now, we can see that in the next slide, using the transform scale, a square flow net is drawn, that is the A part, the figure will have both A and B, and A side is the transformed one. You can see this one is the transformed one and this is the original one. So, and then I am going to this, drawn an NF and ND are obtained. If we consider a square in the transform flow net, it will be as shown in figure A, which I have shown already. The same figure drawn to natural scale, that is x and z, that will look like figure B. That means, if you draw, suppose natural scale looks like this, and when transform it looks like this. Then as let K E be the effective permeability or equivalent permeability for that anisotropic condition. When it is an anisotropic condition, what is the value? That is actually suppose K E, one value, so K x and K z is there, but my intention is to use one value only. Then that is suppose one value which will be used, suppose that is K E. Then from figure A, I can write this equation, that is, since it is a transform section. So, A into K E into del H by A. So, A K and this is I. So, del H by I. So, that means over a distance A, the head loss is del H. So, this is also A, that is actually area if I take unit height, and so this represents A area, and this represents actually I, and this represents K. So, this one if I do that, this A get cancelled. So, that K E into delta H become the Q, and if I consider the figure B, that means original one, then your Q become A times, that is again same, because your flow taking place through height actually A is same, and your K x is the permeability, and your delta is the head loss, and your distance over which it is head loss is taking place, that is A times K x by K z. In the figure B, we can see in the figure A times K x by K z. So, this is the distance x. So, if I do that, so A K x del H by this, now we can see once again this A and A get cancelled, del H is there, and this K z will come here, and these K x and K x it become under root K x. So, that means, the under root K x K z delta z. So, once I am getting Q equal to under root K x K z into delta H, once I am getting original transform section, which I have represented by equivalent or effective permeability K E, then that is I am getting K E into delta H. So, these two must be equal, because I am satisfying certain condition, I have chosen this K E. So, these two flow must be equal, and if these two flows are equal, since del H and del H are both cases are same. So, K must be equal to under root K x by K z. So, that means, whatever I have shown previously, that equation, when this equation again will be valid. So, when you are transform the section, the same equation is valid, only modification will be where that k will be replaced by k e, which is equal to under root k x k z. So, that is the only difference from the one. Now, if this is the one, this is another thing I want to introduce here. After actually effective stress, I will do more elaborately, but here I will just briefly I will try to since hydraulic gradient is causing the flow, there is a term called critical hydraulic. What is the critical hydraulic gradient? If it is beyond critical hydraulic gradient, there something happened in the system. So, because of that our critical hydraulic gradient has to be less than that. So, what is critical hydraulic gradient, that we will examine, and how to find out that what is their expression, we will try to see through this explanation. So, this is actually soil sample, and this is connected through this tank suppose, and water is here, and this is again at this level there is an opening, and water can be collected from here, and if water level is here and it is connected, then this water will try to flow through the soil upward direction, and since this is the maximum level water can retain. So, rest of the water will go out. So, that means when this flow is taking place, what is the head under which the flow is taking place? This is the H, because this is the maximum head here and maximum head here. So, because of this difference at this and this, the flow will take place, and here actually above sample water soil, there may be height h, capital H, and soil height is length is L suppose, and this H. So, then the total head of water above the base, that means at this point, is H plus H, H plus H plus L. So, these three together is the total head acting below this. Now, and head water in the sample above the base, and from this side, if I consider from this side, that is the one, and if I consider this one from this side, how much head is acting here from this side, that will be nothing but H plus L, H and plus L. So, because of some weight acting this direction and because of the water head from this bottom. So, that two will be, one is upward direction and is bottom downward direction, that they will try to balance. So, how long it will be balanced and when it will be unbalanced, that to be obtained. So, therefore, the excess hydrostatic pressure acting on the base of the sample will be gamma w times H. So, if I subtract from here to here, then excess hydrostatic pressure, this minus this. So, H gets cancelled, L get cancelled, only small h is there, and that is small h into gamma w. So, this much excess hydrostatic pressure is additionally from the bottom acting. If it happens, then what is the problem? Problem is here, if any friction between the soil and the side of the container is ignored, that means what is this? So, there is no friction at this here at this wall. So, only if there is a friction, when I consider equilibrium of force, I may have to do equilibrium frictional force, but here since is the quantity and force everything is small, almost static. So, we assume that because of this opening through the voids, water is flowing without causing much force on this entire mass. If I consider that, then I can ignore the friction. So, if I ignore that, then what happens? Then the soil is on the point of being washed out when the downward force equals the upward force. So, upward force is how much and downward force is how much. So, downward force will be equal to buoyant unit weight into volume. So, buoyant unit weight we have derived before, submerged unit weight we have derived before, gamma b will be equal to G s minus 1 by 1 plus E gamma w. This is the thing we have derived before, and So, buoyant unit weight multiplied by volume, that A is the cross sectional area of the soil and L is the length, then this volume. So, that will become the total weight coming from the upward direction, additional water, and an upward force which will be equal to H gamma W into A. So, that is the excess hydrostatic pressure in the downward direction because of the difference in head is acting. So, that is additional. So, these and these must be equal. So, if you want to make these two, so A get cancelled, and then ultimately you can see that H by L, which is nothing but I, will be equal to G minus 1 by 1 plus E. So, this is the expression, that means, hydraulic gradient we are getting G minus 1 by. So, this is the critical. Why it is critical? Because we have just considered the upward force and downward force is just equal. So, that satisfying that condition, whatever critical hydraulic gradient we have got, that is the critical hydraulic gradient. Why it is critical? Because if I increase the head, if I increase the head, if I increase the head, okay, if I increase the head this side, then hydrostatic pressure will increase. So, H to H 1, then it will increase the pressure, and if that pressure become more and more, there will be a time, sometime, because of this excess pressure, the soil will be washed out this side. So, that is the why, that is the reason we have obtained this critical hydraulic gradient. If the hydraulic gradient become more than that, then your soil will be washed out, that means will move upward direction. So, that is what, this is a very important relationship, hydraulic gradient with specific gravity and void ratio. So, once you know the specific gravity and void ratio of soil, then one can find out the hydraulic gradient, that is the guidelines which has to be your critical hydraulic gradient has to be hydraulic gradient has to be less than this. So, if we do that, then that has to be satisfied. So, now what I will do, I will try to take one or two problem here to apply whatever concept we have got, and some application one by one. So, this is one application. A large sized excavation is made in steep clay